Hi, people. Yes, this is not your next slide, but now that you've gotten some experience with a typical, I don't know, acceleration kind of problem, or what we call a kinematics problem, not a bad time to talk about some of the things that might be challenging. One of them is that the quantities involved in kinematics equations, or most of them, are vectors, right? Meaning they have direction associated with them. And in some cases, like you've seen, we need to account mathematically for the fact that vectors can point in opposite directions. Yeah, so for example, you saw a question like this one. This ball is going one way at notice a speed of 10 meters per second. Yeah, and then something goes it ends up going in the opposite direction at 8 meters per second. So what we can say here is we can say that some initial velocity is 10 meters per second, but the final velocity is 8 meters per second in the opposite direction. That's how we take care of direction. I'll say use of sign. Okay, so be on the lookout for those cases. Next. Oh yeah, third. Yeah, these are, this is, I don't know how tricky, but sometimes a question will say, with an initial velocity of something meters per second. Sometimes questions will just, let's say you just, I don't know, out of the blue saw that. And you say, gee, which given is that? Well, you ought to be able to tell, ideally, what shows up here? Ideally, from the units, right? We ought to say, 3.5 meters per second squared. Oh yeah, that's an acceleration. Use the units. All right, I don't know how helpful this is, but something you can try to make use of. The other thing that can be tricky with these, and you guys have seems like you've done quite well with this already, is that not all givens show up as numbers. All right, it's easy when you can look through a problem and say, oh, there's a 10 meters per second. I know that's a velocity. There's like we said before, there's a 3.5 meters per second squared. That's got to be an acceleration. But sometimes there aren't numbers and there aren't units to identify what some given value is. But there are a couple of cases, and this has 5 rows. I don't really know that there are 5 of these. But what I'd like you to try to come up with for me are words that mean an actual numerical value of some quantity. Okay? What phrases have you seen in a problem that tells you exactly the value of a certain physical quantity? All right? See if you can come up with these. You should be able to come up with at least 2 of them. Okay? Okay. Now, I'm going to show you a harder problem. All right? This is a classic kind of problem called a cop and a speeder. And here's what happened. A car is speeding. That's our green car up top. It speeds by a speed trap, and it's moving at that speed, 40 meters per second. At the instant the car passes the cop, I guess the cop knows he was speeding, so as the instant he passes him, he begins accelerating at that rate, 5 meters per second squared, to chase the speeder. How far does the cop travel before he catches up to the speeder? And how fast is he going? So it looks something like this. Notice we've got that car going at a nice constant speed, right? But when he passes the speeder, the cop accelerates, and whoop, eventually right there, look, he finally caught up to him. All right, but notice the car moves at a constant speed. The cop accelerates. All right? So how far does the cop travel, and how fast is he going? There's a lot of things we don't know here. Okay? So this, whether or not you know it, is called a two equation. Two unknowns. known problem. Okay? And what I'm going to start doing is thinking generically about what we can say about the motion of each of these objects. All right? I'm going to talk about the speeder, and I'm going to talk about the cop. In general, we can talk about what the speeder does. Well, the speeder moves at a constant velocity, and therefore we can write an expression for how far the speeder travels. Well, that depends on how fast he moves on average and the amount of time that he travels for. Right? Because we know this thing moves at a constant speed, we can write a nice simple expression for his change in position as a function of time. Okay? We can do the same thing for the cop. We can say that the cop travels some, or has some change in position, but he doesn't move at a nice average constant velocity. What he does do is start at rest, because he's sitting there in the speed trap, and then accelerates at that some constant rate. So we can say that for the cop, we know his initial velocity, the amount of time that he travels. We know his acceleration, and that same amount of time that he travels for. Now, cop, 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 cop. The other thing I would say is this. That can be a real helpful thing for you, right? This cop starts at rest. Doesn't say that explicitly, but you have to assume that the cop is sitting there, you know, the old radar gun pointing out. So we have this expression for how far the cop goes, just 1/2 AT squared, and this expression for how far the speeder goes, V average times T. And then we have to say, well, there's two equations with two unknowns. We don't know how far the speeder went or for what amount of time he traveled. We don't know how far the cop went or for what amount of time he traveled, but we do know that we can connect them because it says, look, he catches up to the speeder. So that means that at some instant, delta x speeder and delta x cop are the same thing. Now that's true when the time that the speeder travels is the same as the time the cop travels. Okay? So when the cop has traveled for some amount of time, well, he has the same displacement as the speeder has. Well, that also is when they've traveled for the same amount of time. Okay? So that means we can take these two equations and set them equal, because this and this are the same. So we can say V average speeder times T equals 1/2 a cop times T squared. Now notice, I dropped T speeder and T cop because they travel for the same amount of time. Now, sure, the speeder was traveling for some amount of time prior to the time that the cop was accelerating, but when we say T cop, we talk about the time that he was moving. And during that time interval, there's the same amount of time that passes while they get to the same displacement. That means we can, with some algebra, do this. And notice, we want to know how far does he go. Well, we don't have that expression yet, but what we can do is figure out how long it takes before these guys catch up to each other, or before the cop catches up to the speeder. 2v speeder over a cop. 2v speeder, that's 80 meters per second, divided by 5, that's 16 seconds. Now notice, if you put t into there and t into here, you're going to get the same thing for the delta x for each one. You better. 16 times 40 is what, 640? And then 16 squared is, I don't know, 256 times 2.5, I don't know, yeah, 640 also. Give it to yourself if you want to. Okay? And then you find this for me. How fast is the cop going? Okay? So that's you. Now I think the question at the number 6 so number 6 on the bottom of your acceleration and big uglies. When I say big uglies, I refer to those equations. We call those the big uglies. So when you, that number 6 is the same question as this one with different numbers. All right, so what you might want to try to do is see if you can solve that one without looking at this one. Fair enough? We'll look at a couple more 2 equation, 2 unknown problems when I see you tomorrow in class. All right, folks? Happy Monday night.